Okay, we're going to continue on here. Chapter 12, I think. Maybe. All right. So we were talking about kinetics, and we talked about some specific orders of reactions. We had our first order reaction, which again has rate constant units of reciprocal seconds or 1 over some unit of time. It does have sort of an integrated rate law, which is concentration versus time. Natural log of A equals natural log of A naught minus KT. Also a half-life sort of equation there, natural log of 2 over K. It has a specific sort of graph that's associated with it, and that is the natural log of A versus time. That is achieved by rearranging this equation in the form of y equals mx plus b. That should give you a linear sort of line where the slope of that line does equal minus the rate constant. Again, should end you with a positive rate constant. We also saw second order there. And second order has the units there for the rate constant of 1 over molar seconds. Once again, in terms of time, it really could be any unit of time, but seconds is pretty common. 1 over A is equal to 1 over A naught plus KT, a little half-life action there. 1 over AK there. And we have our graph here again from rearranging that there, which would be the 1 over A versus time. This is going to yield us a positively sloping line where the slope there is equal to K in this case. We also saw a zero order. And that has units that is the same as the rate, as obviously anything to the zero order will equal 1, and that leaves you basically that the rate is equal to the rate constant. Also has a sort of concentration time law formula, similar to first order, except no natural logging happening there. Also has something like this, perhaps for the half-life. And here, the typical graph for that is concentration of A versus time. Once again, yield you a straight line with a negative slope where it equals minus K. So as we talked about before, it's really important to understand the units associated with the rate constant, as they will tell you what order of reaction you're dealing with so that you can use the sort of proper formula. Um, Once again, a lot of problems will not just tell you what the order is. They'll just assume that you can kind of know what it is based on those units as you see with the K value, if they give you the K value. The other thing we talked about is sometimes you do need to sort of use these together to solve a problem. And again, in that situation, usually you would not be given the rate constant, but perhaps be given the half-life, and you can use that to get to the rate constant as well. Other things that sometimes pop up, percentages can go in here as well. Yeah, so if you have 100%, that would be like your initial, right? And whatever is left over at that point, you got 25% left, that would be, your final and stuff like that. So you can, we do think about sort of molarity a lot going into here, as we'll talk more about when we get to the nuclear chapter. Really, you can put any unit you want on both of those A's as long as they're the same units. So like I said, sometimes you may come across something like percentage or something like that, where again, you could use 100% and whatever the other percentage is. You could also use, in addition to that, if it is a percentage, instead of 100%, you use 1 and point something for the other sort of percentage, and use it more like a decimal form as well. So you technically can put any values in there for A. They actually could be, as we'll see when we get to nuclear chemistry, things like grams, milligrams could go in there. Things like radioactive decay rates and stuff like that. So, but mostly we'll deal with concentrations here in this chapter, I think. Any questions on any of that there? I could just flip this slide on. All right. So here's pretty much what I just wrote there. It's a nice little summary slide and pretty much everything that you do need to know. Again, those kind of concentration time equations and the half-life, and obviously the graphs that go with it as well. All right, and obviously we can use those three graphs, and if you weren't sure what the order of the reaction was, but you plotted all three of those graphs, you would do something like a best fit line, and whichever one had a higher R squared value closer to 1 would be the most linear, and that would be the order of the reaction. That's something we'll do in the next experiment, actually. It's a bunch of graphs. All right, so next thing we're going to talk about is energy and temperature and sort of how it affects the rate constant. And these are two energy diagrams that you may be familiar with. This is our reactants here. That's our products. This is our reactants on this side, and that is our products on that side. So the first graph here on the left shows a exothermic plot, and you may be familiar with exothermic. That is when energy, thank you, is released from the reaction. And we see that because essentially, if we look at the energy difference between where our reactants are and our products end up, they kind of have to give off energy to drop down in terms of energy to get to the products, and energy is being given off basically as a result of that. So whenever you look at an energy diagram like this and the reactants are higher in energy than the products, it should be an exothermic reaction, as opposed to an endothermic reaction where we absorb energy. Right here, we release energy. And the opposite is true in this case. Our reactants are actually lower in energy than our products. So again, the only way to kind of get our reactants up there in terms of energy is to put energy goes in to do that. And that's an endothermic reaction. So in a chemical reaction, basically the only thing that happens is all of our reactants basically break their bonds, and then they kind of reassemble on the other side with new bonds. We have conservation of the elements, right? Because we do not do anything with the nucleus in a chemical reaction. It's all about bonds, it's all about electrons. And as you hopefully know, right, the thing that determines what element you're dealing with are protons, the atomic number for the periodic table. So because no chemical reaction does anything with the protons, if you start with 4 carbons, you end with 4 carbons. They just may be in different things at that point. So what happens for a reaction to take place is really kind of two things has to occur. There usually has to be a collision, so the reactant molecules need to kind of come together. They do need to come together in sort of the appropriate spot on each of them. That's sort of like the activated spot there is where they have to kind of hit each other. And secondly, when they do sort of come in contact with each other, they do need to have the right amount of energy in order for products to form. And that sort of right amount of energy, in a sense, is what is known as the activation energy. The activation energy, which is E of A, is the minimum amount of energy required for a reaction to take place. So not all collisions of reactant molecules will result in products being formed. They have to meet those two things. They have to hit each other in the right spot. They have to have the right amount of energy to really start initiating, breaking the bonds and stuff like that. The activation energy here, as you can see, is the hill between the reactants and the top of the energy diagram right there. And that is what is sometimes referred to when we get to the very top is this is right here. That's what sometimes referred to as a transition state. So this hill that the reactants has to climb in terms of energy to get to the other side is known as the activation energy. At the very top of that hill is where you find the transition state. You will also find this little complex right here. This guy right here with the little symbol right there. That is what is sometimes referred to as a transition state complex or a activated complex. And basically what is happening is as the reactions start to progress down the road here, they're starting to break bonds, but they're also starting to make bonds. So as it kind of creeps up the hill there, we're starting to kind of break up away the bonds that we originally had. We're starting to form some new bonds. And when you get up here to the transition state complex, you typically have something with partially broken bonds and made bonds. So when you reach that transition state complex, That is what you have. You have this sort of intermediate. Now, as you probably know, if we look at just the energy toll of everything, that transition state complex is found at the very peak of energy in this reaction, right? And in chemistry, when things are in high energy, is that really what they want to be? No, right? Pretty much everything we do is to kind of lower the overall energy to get things more stable. Things in high energy is really not very stable situation. And that's why very quickly, usually, it'll kind of come down the hill the other side because it's this really sort of intermediate where you got sort of partially broken bonds, partially made bonds, and then doesn't really like to be that way because it's very high in energy and it usually will come down very quickly. That's why a lot of times in a lot of reactions, it's very hard to isolate that little intermediate because it doesn't hang around a very long time because it's sort of that transitional sort of period along the way. And we see the same thing here as we sort of climb the hill for our endothermic. We do see, again, starting to break bonds and make bonds until we get to our transition state up here and our transition state complex. And again, it's going to come back down. Now, we know that this is a exothermic and an endothermic reaction based on the position of our reactant and product molecules. And as you may remember, one way that we display that is with delta H, which is the change in enthalpy. It's basically the heat of a reaction. The way that we calculate delta H, as a reminder, is basically the delta H of the reaction is the delta H of our products minus the delta H of our reactants, right? Kind of look those values up in a table if you needed to, and take all of your products minus all of your reactants. And we typically will see a delta H either being a negative number or the delta H will be a positive number. And if the delta H is a negative number, is that an exothermic or endothermic reaction? It is a exothermic reaction, right? If you end up with a negative delta H. And if you have a positive delta H, that's going to be a endothermic reaction. So how do we get that from the graph? Hopefully you also know that if you take the difference between where the reactants are and the difference in energy of where the products are, that difference is your delta H, right? That's how you calculate the delta H. And if you can see here on the left-hand side, the delta H of the reaction, my delta H of my products is a small number in terms of energy minus a larger number in terms of an energy. So if you take a small number minus a larger number, you will end up with a negative value for delta H, which is why it becomes negative. And if you look at the delta H for this reaction, and again, is the difference between your reactants and your products. And in this case, if you calculate delta H of the reaction, our final state, which is our products, is larger in energy than our smaller reactants. And that will yield you usually a positive value for delta H. So when we see delta H, if it's a negative exothermic reaction, positive endothermic reaction, and again here, this reaction is either exothermic or endothermic. Now, obviously, as you could probably see, when we look at the hill here in terms of our activation energy, this hill would have a pretty good effect on the rate of a reaction, right? So the bigger the hill, less molecules are going to have enough energy to get up and over to the other side, most likely going to have perhaps a slower reaction than if you had a smaller activation energy hill, because again, more people could get up and over to the other side, right? So it's like if you walked a giant hill to get to the other side of campus, not very many people are going to want to go do that. But if you just have like the little speed bump in the parking lot to get up and over, everybody's right, going to walk up and over that to the other side. And a lot more people and a lot more reaction would occur a lot faster. That's also why endothermic over here, right? Because you need a little extra, right, to get up here as our endothermic activation energy is a little bit bigger of a hill. So you need that little input of energy to help everybody kind of get up and over to the other side. Any questions on that? One way to speed up a reaction, as you may know, is to add a catalyst. So we can add a catalyst. And when we add a catalyst, once again, it is not a reactant. It is not a product. And it does not get used up in the reaction. It is there really simply to allow the reaction to occur faster. How that affects, say, our energy diagram is we had our energy diagram here of, say, our reactants to products here. And if we were to draw our activation energy here, it would look something like this. So when you add a catalyst to a reaction, in most cases, the catalyst is there to speed up the reaction. And again, a catalyst could be in the same phase as everybody. It could be aqueous, like you could have a catalyst that's like an H plus or something like that. You could also have a catalyst that's like a metal or something of that nature. So if everybody again was sort of gas molecules, and you had this metal here, and without that metal being present, that catalyst, these gas molecules got to keep flying around until they come in contact with each other to basically start a reaction, right? So they got to sort of happen upon each other. So sometimes something like a metal will attract everybody towards the metal. And once again, what that's going to do now is put those molecules very close to one another and going to sort of initiate their contact, and also can help in some cases with like the breaking of some of those bonds as well, and sort of allow these things to come in contact a lot faster. So it finds an alternative pathway for that reaction to take place. Ultimately, what it does to your energy diagram is it lowers the activation energy. So if this was a catalyst, the activation energy here gets much smaller. So now a greater proportion of molecules will have enough energy to get up and over to the other side. The result of that is you do see an increase in the rate of the reaction. Any question? So let's talk a little bit about the effect of temperature on the rate. One of the things that definitely will affect the rate is the temperature. And when we change the temperature, what we're really doing is one of two things in most cases. If we increase the temperature, we're adding a lot more energy to the system, right? And that's good for everybody because now everybody has a lot more energy. Also, things are moving around a lot faster, which would initiate more contact and collisions to occur, and usually will help with the rate of the reaction by speeding it up. Alternative to that is if you kind of put everything on ice, it's like removing energy from that system. By doing so, everybody's going to have less energy, going to kind of slow down. And now they're going to probably have less collisions. And if they do have collisions, they might not have enough energy to really kind of initiate that reaction to take place. So there is sort of an Arrhenius factor here that shows that relationship. This is our rate constant. That's our frequency factor. That's our activation energy. That's our gas constant, and that is our temperature. By the way, in this formula and some other versions of it we use more often, R in this case is the gas constant that involves basically energy. So it is not the 0.08201 that you used or 206 that you use for the ideal gas law. By the way, activation energy is always a positive number. So when you calculate the activation energy, it's always a positive number. If you look at any of those graphs that we were just looking at, that's the activation energy. So it's always a positive number. That's sort of heal in terms of its value. Now, one of those things that happen on that activation energy again is the activated complex or a transition state. And again, that is something with sort of those partially made bonds, partially broken bonds that you get when you get to sort of the peak of the energy, sort of for that particular reaction. This is very high in energy because it contains those partially broken bonds, partially made bonds. Now, for example, here, if we had this, it can rearrange and the carbon and the nitrogen can actually switch places. But what happens is we start to weaken this bond here and we start to rotate this guy so it can make a new bond that is coming into this reaction. So this activation barrier there When we get to the top, we got these partially made bonds, partially broken bonds, and then it comes down to our normal product on this side versus our reactant over there on that side. So, although that is the Arrhenius equation, most people do not use sort of that equation. We sort of use a natural log version of that equation. But what we do see in terms of the rate constant and temperature, when you have a lower temperature, your rate constant is smaller, right? As we see there. When we increase the temperature, we do see an increase in the rate constant. It gets larger as we go across. Now, taking that top equation and kind of natural logging everybody gives us this version of the Arrhenius equation, which is a version we do use. Now, I will say that this version of the Arrhenius equation is sort of like the graphical version of it, if you will. And that's because if we take it, the natural log of K is equal to minus E of A over R, 1 over T, plus the natural log of A. This is written in the form of everybody's favorite thing, which is a straight line. This is y is equal to mx plus b. There we go. So on the x there, we have the 1 over t, and on the y will give us the natural log of k. We can use this to graphically solve for the activation energy by taking the slope of this line. The slope of this line equals minus E of A over R. You basically can multiply R to both sides, and that will get you your E of A. Now, again, as I mentioned, the activation energy is a positive number. That is because when we look at a line in this direction here, that is a positively sloping line or negatively sloping line? Negatively sloping line. So the actual slope value you would get from the graph would be a negative number, and that's why there is a negative here. Again, those two negative numbers will turn your activation energy into a positive number, which it should be. So activation definitely should be positive. And again, 8.314 is the version that we're using there. And this also shows sort of the difference between temperatures. So here at the smaller temperature, our lower temperature, which is the blue temperature, we do see basically this for our fraction of molecules that have enough energy to get to the other side. But when we increase the temperature, we actually do see a pretty big increase in terms of the number of molecules that have enough to get to the other side. So definitely by increasing that temperature, we're going to see a lot more activity and things will have a lot more energy to get up and over to the other side. All right, so that's our plot of our straight line. Let's take a look at one here. So this is a typical sort of problem that you may be given in the homework. And as I mentioned before, there's definitely some problems in chapter 12, the kinetics chapter, that you just got to kind of lay up some Excel graphs and stuff like that to answer, or some type of graph to sort of answer it. So again, if you come across a problem, you're like, I'm not really sure what to do here, it may be something that you have to kind of make a graph to sort of answer. So here is typical. In this case, they're actually really nice to you. A lot of times in these tables, you'll have the temperature given to you in Celsius. You have to do the conversion to Kelvin. And here we do have the rate constant given to us. So what we would want to do in this table is we would want to convert each of these values into the natural log of K. And we would also want to take 1 over the temperature. And again, we would want to make sure that that's in Kelvin. And what that's going to give us is the plot that we typically plot for an Arrhenius plot, which is the natural log of K is equal to 1 over the temperature in Kelvin. And again, that's going to yield you a sort of negatively sloping line in this particular case. So if you did all that here, you would end up with a graph that looks something like this. And you would end up, obviously, you'd do a best fit trend line, you get your R squared value in your equation, and you would end up with an equation on this. So with that information, why don't you determine the value of the activation energy and the value of the frequency factor, which is A. So take a moment based on this information and calculate both of those things down. Okay, so let's take a look. So once again, here we can, obviously, if this graph wasn't provided for you, you would need to make your home graph. I'm assuming on an exam or quiz, maybe the graph would be provided for you. I don't think I'll have a hand graph or anything, but for the homework problems, you again may need to make the graph. So we want to use, again, this is coming from really the equation that we just saw, which was the natural log of k is equal to minus e of a over r, 1 over t plus the natural log of a. And again, that is our y is equal to mx plus b. And once again, on the y, that is why we're graphing the natural log of k. On the x there, that is why we're doing 1 over the temperature. And once again, the slope of this line will equal minus e of a over r. So the slope is equal to minus e of a over r. Here, our slope would be here, and it is a negative number, 1.12 times 10 to the minus 4 equals minus e of a. Once again, it is the one with energy here, 8.314 for our R, joules per Kelvin per mole. We're going to basically multiply that to the other side. But in addition, we also have the negative that needs to go over there as well. So that will get us 1.12 to the minus 4 times 8.314. And we will end up with, punch that in right, 1.12 to the 4 times 8.314. There we go. That's going to give us an E of A of 93116.8. By the way, the units here are going to be joules. Typically, activation energy is given in kilojoules. So if you divide it by 1,000, you end up with 93.1 kilojoules, which is the typical units associated with the activation energy. Again, here a positive value, not a negative value. There's not any questions on that one there. In addition, we can solve for the frequency factor, which is A, and we can see from our equation that the natural log of A, which is equal to our B value here. So right there is our B value from our equation. So the natural log of A is equal to 26.8. To get rid of the natural log, you're going to do E of both sides, right? Is that for you? And if you do that, we will end up with about, let me try this again. I'm not doing great on my calculator today. Try this again. Hit the right button might help. There we go. That looks more like it. All right, 4.36 times 10 to the 11. Now, people often ask, like, hey, what is the units sort of associated? Yeah. Yeah. Where to go? Oops. This part here? How we got that? Is that what you're asking? Or, yeah. Yeah. So basically from actually going back here, from this equation here, this is in the form of y is equal to mx plus b, which gives us that straight line. So what's plotted on the y is the natural log of k. What's on the x is 1 over the temperature. That means if we look at the slope here, the slope of that straight line that you get will equal minus E of A, which is the activation energy over R. R is the gas constant. And again, in this case, we're using this version of it. So we really have this, and we could get this from the actual graph there. So if we go back to that graph, what we see is from the best fit line equation, right there is our slope, basically. It's the one in front of that. So basically, we just plug it in there. It's just 1, 1, 2, 4, right? So basically here we have 1.12 times 10 to the 4, and that was negative equals negative E of A divided by 8.314. So we're going to multiply that to the other side, and then also divide by the negative 1 to the other side, or however you want to get rid of the negative at that point. So, yeah. I asked the math what I did to get there. Yeah, so I did E of A would equal 8.314 times my negative 1.12 times 10 to the 4. And I also have this negative here, which however you want to think of it, you could divide by -1 if you want. So you just kind of change the sign. No, and that should get you, yeah. There is, and we're going to talk about it next. There is a sort of non-graphical version of this, and so there's kind of a graphical version, which is typically what this is used for. This is sometimes referred to as sort of the graphical version of it. And then there's a form that we'll see in just a second, which is sometimes referred to as a two-point version of this equation. And what that means is basically you're taking 2 points along that line that you would normally draw and solve it with that formula that we'll see. Yeah. This right here? Yeah, so that A right here is the frequency factor. It is actually like the proportion of molecules that kind of have enough energy to get up and over the hill to the other side. Yeah, it's basically what that is. Yeah, yeah. It is definitely not absorbance in this case. It's basically related to the amount of molecules that have enough energy to basically get over that activation energy hill. Other questions? Uh, for the A, is that what you're talking about? The EA was 93116.8, and those were joules. If you divide it by 1,000, you get kilojoules. So make sure you are using your exponent button when you punch the 1.12 and hit the exponent button. And I think I wrote a negative here, which should be a +4. I think I put +4 in, I think, but just to double check. Yeah. Other questions? All right, so where we were was here with our frequency factor, which is what A is, and people ask sort of what are the units associated with it. So basically, the units associated typically with the frequency factor are usually the same units that are associated with the rate constant. So when you take kind of the natural log of the K, you lose the units. When you kind of take the E back of it, the units come back, and that's essentially what we just did there. When we take this E, we're going back to units. So typically, the unit associated with it will be the same as what you see for the rate constant, which in this case is m to the -1, s to the -1 would be the units associated with it. Question on that there. So again, this is sort of the graphical version of this equation that you could make a graph or the information that you could get from the graph, the activation energy and the frequency factor. Now, the question I was just asked is, will we always make a graph? And the answer is no. Most of the time, I would say probably when you're using the sort of this Arrhenius sort of version of the equation, you'll use this 2-point version. And like I said, basically what the 2-point means is you have that line from that graph we just made, basically, and you're going to choose, basically it's going to kind of choose 2 points along that line to basically calculate. Now, this particular equation here, I'll be honest with you, there's like 3 different versions of this formula that you'll see as you go around. Even the lab manual, I think, uses a different version than this one. But if you use any legit version of it, and there's about 3 different versions, it will come out okay. So what is this? This is basically 2 points along that line. And if you have basically the K values, the rate constants, you can put it in there. So that's rate constant number 2 versus rate constant number 1, natural log. That's our E of A, which is again our activation energy. That is our same gas constant, which is 8.314 joules per Kelvin per mole. These are our 2 temperatures, which is those rate constants come from. Do need to be in Kelvin. Now, it's really important in this equation that you are careful of units because right here is a problem for a lot of people. And that is because, again, typically speaking, activation energy is usually given in units of kilojoules, while R is basically in units of joules. So you're 1,000-fold off there if you don't do a conversion. So you do need to usually either convert the kilojoules to joules or the joules to kilojoules. But if you leave them just the way they are, you will find yourself like 1,000-fold off there because of that conversion. So that's a very common mistake. Other common mistake, again, is not converting the temperature here into Kelvin and put them in Celsius. And that happens a lot because, again, sometimes you are asked for maybe what the temperature is in Celsius, and they give you the other temperature in Celsius, so people think you could just kind of put it in Celsius. But you do need to go into Kelvin and then convert it back to Celsius at the end. Do you have a question? Say it one more time. Correct. So this would be, I would say, probably the equation you use most of the time. Um, and this would be an equation that basically you could use as long as you got basically 2 points along that line, information, basically either a couple of rate constants, a couple of temperatures, and a rate constant, something like that. So in this particular case, you could solve for really anything here. You may be asked to solve for a rate constant. You may be asked to solve for the activation energy. You may be asked to solve for a temperature. So any of those things you could use this equation to solve for if obviously you have the other pieces of information along the way. Like I said before, there are a few different versions of this equation. And one that really confuses people sometimes is the negative. Yeah. And um, in this particular version of the equation, there is no negative um, out here in front. So people oftentimes will remember the graphical version of it where there is minus E of A over R. And in this particular one, there is no negative. To further complicate things, like I said, since there are three different versions, there actually is a version where the negative is on the outside, but the temperatures are switched inside. And there's also a version where they will combo and combine the bottom two temperatures, do like T1 times T2 and have a different version up on top. So again, there are a few different versions. I would just stick with maybe this one and just roll with it when you have to use this equation because there's little things sometimes confuse people when they kind of see the different versions and stuff like that. All right, so why don't we try one here? Let's find the activation energy. If we have this reaction, we have a rate constant of 2.57 at 701 Kelvin and 567 at 895. So what will be the energy? Okay, let's take a look, see how you're doing. So just pull out some information. We got a rate constant here of 2.57 and a temperature that kind of goes with it of 701 Kelvin. We got another rate constant 567 and a temperature that goes with it of 895 Kelvin there. And that is all we got, I think. All right, so you could really call these whichever way you want to go. You could call these ones as long as they stay together. The numbers that go together, or again, you could swip them around. It doesn't really matter. We're good here as we're already converted into Kelvin. We could use our natural log of our K2 divided by K1 equals E of A over R 1 over T1 minus 1 over T2 in this case. So putting in our numbers here, natural log of 567 divided by 257 there, 2.57 equals E of A. Again, R a constant at 8.314 joules per Kelvin per mole. 1 over our T1, which again is already converted into Kelvin, which is good, minus 1 over our 895. All right, so clean up the left-hand side here and maybe clean up this as well. So left-hand side, remember you want to divide first the two numbers and then take the natural log of it. And that's going to get you 5.3964-ish equals E of A 8.314. And if you clean up what's in the parentheses there, 1 divided by 701 minus 1 divided by 895, that's going to get you 0.000309215. Mathematically, we're going to divide that to the other side. And if we do that, we will end up with basically 17452.10 equals E of A over 8.314. Obviously, the last thing to do there is multiply that to the other side. And that's going to give us an E of A, which is about 145,097. These are going to be joules based off of the joules there that was in our R in this case. Divided by 1,000 gets you about 145 kilojoules in this case. Yeah. Any questions on that there? Once again, positive value for our activation energy. Any questions on that one? Okay. Let's take a look at another one. Actually, let's do this one here. Let's just do one I make up. Let me see. I think this will be better. All right. I have some numbers, I think. So let's see. For the following reaction, we'll just do A plus B goes to C. Very creative. Has a rate constant of, we'll go with 5.5 at 35 degrees Celsius and a activation energy of 45 kilojoules. What would be the temperature in Celsius, degrees Celsius, when the rate constant is 11? We'll do here. I'll do reciprocal seconds for the units there. Reciprocal seconds on each of them. All right, give it a go. We'll hope for the best. Yeah, it comes up there. Yeah. At 35 degrees, the rate constant is 5.50 reciprocal seconds and 11 reciprocal seconds at the other temperature. Activation energy, 45 kilojoules. Yeah. Hope those are the right numbers. We'll see. Constant there, 550. And we got a temperature goes with this 35 degrees Celsius. We are looking, we got another rate constant of 11. And we're looking for the temperature. We do have E of A, 45 kilojoules. And we do have R that's always sort of available to us. So once again, looking at our formula here, K2, K1, E of A over R, 1 over T1 minus 1 over T2. We do need to do conversion here of temperature. So we got to go 273 plus our 35, going to get us a 308 on the conversion there. 308 Kelvin. Other than that, we could kind of put some numbers in. So we'll go natural log of 11 here. I'm just going to call these, I guess, ones and twos. Go that way. Over 5.5 equals our E of A, which is 45. I'm going to multiply it by 1,000, and I'm doing that to convert it into joules. And the reason I want to do that is the R is in joules. So once again, if you leave the top in kilojoules and the bottom in joules, you're going to be off by a factor. Or you could convert it the other way and convert the other guy into kilojoules, whichever way you want to go. But you do need to make sure those two guys are the same units. 1 over our 308 it was there, minus 1 over our T2 at this point. All right, so just going to kind of clean up a couple things here. We'll go clean up the left there. 11 divided by 5.5 is 2. Natural log of 2 is 0.693. Over here, we got 45 times 1,000 divided by 8.314. Going to get us 5412.557. Still got 1 over 308 minus 1 over T2. We're going to divide that to the other side, right? And if we do that, we will end up with, looks like 0.000128063 equals 1 over 308 minus 1 over T2. We're going to take this and subtract it to the other side, right? So we're going to minus 1 divided by 308. That's going to give us a negative 0.003119 equals negative 1 over T2. We're going to multiply that to that side and bring this back the other way and divide it, basically. And when we do that, we will end up with basically 1 divided by that 0.003, and that's going to give us a T2 that is 320, we'll call it 20.6. This is Kelvin, as obviously this is in Kelvin, so that's what ends up being there. To get to Celsius, we're going to subtract 273. And about 47.6 degrees Celsius, give or take. Yeah. Questions on that? Yeah. I'm good with 273. If you like the 0.15, you can. It don't matter to me. But I'll go with just the 273. So what we have at that point is that one right there, right? So you got negative, what was it there? So negative 0.003118 equals negative 1 over T2, that part. Yeah. So basically, you got to multiply T2 to both sides, and those are going to cancel. And that'll basically give you negative 0.003118 T2 equals negative 1. You then need to divide this to the other side with a negative on both sides. Those go away, negative go away, and that'll get you there. Yeah. Other questions? So what we see here is something that we talked about earlier. We basically increased our temperature by about 10 degrees, and we see actually the rate constant doubled, right? So it went from 5.5 to 11 within about 10 degrees or so. So for a lot of reactions, if you increase the temperature about 10 degrees, you will see basically a doubling for a lot of reactions of the rate constant. The rate of the reaction will speed up. Any questions on the Arrhenius equation, solving for it? Yeah. All right. All right. So the last thing we're going to talk about in this chapter is reaction mechanisms. And um, now, when we look at a reaction, and as you may know or may not know, not all reactions actually occur per se in just like one step. So when we look at this particular reaction here, you may look at it and think, oh, it must just all kind of go in one step to make our products. And that's not always the case. A lot of times reactions are made up of individual little steps that occur, and then you kind of add them together and you get the overall reaction that's happening. All these sort of little steps along the way are what are referred to as elementary steps in a reaction mechanism. And why do we know that perhaps this reaction does not occur just like straightforward from reactions to products? Because what we do see is when you do this reaction, N2O2 is actually detected in this reaction as it's occurring. It is not there in the overall reaction, which would imply that it had to be made early on to be detected and then had to be used up by the time the reaction's over, which would imply that obviously didn't happen in a one-step fashion. This is very similar to everybody's favorite thing from Chem 50, which is Hess's law. Yeah. We add up all those little equations, put them together, switch them around, and all that kind of stuff, right? To try to build basically one overall reaction that you're looking for in terms of the energy. And that's sort of the idea here. So one proposed mechanism here is we have sort of a elementary step here, our first step of two NOs come together to form N2O2, which might explain why it is detected in this reaction. Then a second sort of step where that N2O2 gets used up to make the NO2. When we re-add these elementary steps together, you basically could cancel out anything that's on opposite sides of the arrow, or you could reduce down things that are on opposite sides. So if it's like a 1-to-1, they could subtract off. If there's more than one and you have one on one side, two on the other, you'll be left with one left over. In this particular case, the N2O2 would completely cancel out, kind of like you're subtracting them off. And then everybody on the left-hand side of the arrow stays there, and everybody on the right-hand side stays there. So that is 1 and 2 of the NOs, and 1O2 gives us 2 NO2s as our overall reaction. So these elementary steps are what sort of builds out the reaction that we're looking at. And this is what is sometimes referred to as a mechanism of this reaction. Now, mechanisms may not always be the way that a reaction occurs all the time. It's just sort of an explanation of how this reaction takes place. So let's talk a little about some things that we do see, and that is intermediates. Intermediates are species that appear in a reaction mechanism, but not in the overall reaction when it's all said and done. So an intermediate is always formed in an earlier step and consumed in a later step. So in order for something to be an intermediate, it cannot be part of the overall reaction. So that can happen. If something gets reduced down, it could still be there at the end, and that would not be an intermediate. So an intermediate in this case, obviously, is our N2O2. It gets completely canceled out. It is not left over when the reaction is done. And that would be something that's formed in an earlier step and then basically removed at the end or before the end is reached. One of the ways that we can describe these sort of elementary steps is by either being unimolecular, which means there's basically just one molecule reacting, bimolecular, which means that there are two molecules reacting, or termolecular, which means there are three molecules reaction. Each of these would be bimolecular, as there are two molecules reacting in each of these steps along the way. Now, one of the things that is different than everything that we talked about up to this point in terms of rate laws is for elementary steps, and only for elementary steps when you're doing reaction mechanisms, you can actually use the coefficients as the exponents for the orders. And that's the only place sort of in kinetics where you can kind of use the coefficients in the equation as the exponents. So for this unimolecular reaction or step, we could write a rate law for it where the rate's equal to K times A. And here we would technically use the coefficient as the order there for A. Here it would be A and B, so the rate would equal the concentration of A and B. Again, they both would be technically based on the coefficients, first order. We run a rate law for this bimolecular. When you put those together, you get 2A goes to products. And that is where the 2 comes from, basically the coefficient here. So this is the only place in kinetics where you can use the actual coefficient as the orders when you're doing elementary steps and these sort of mechanisms. So what is the idea behind this? There's a few different types of mechanism type problems. In order for a mechanism to be a plausible mechanism, sort of a good mechanism, if you will, there's a few things that has to happen for it to be good. The first very simple thing is if you have a bunch of individual elementary steps, when you add up all those steps together and cancel out everything that needs to be canceled out, you should be left with the equation you're looking at. And if you add up the steps and it doesn't match the equation you're trying to determine, then it's definitely a bad mechanism because it doesn't add up to the equation you're looking at. If you add up all the steps and it does add up to the equation that you're looking at, then so far that mechanism is a good mechanism. The other important part of the mechanism is what is referred to as the rate determining step, which is sometimes abbreviated as the RDS for rate determining step. It should have the rate law that is the same that is found experimentally. So in these mechanism problems, sometimes they may give you the experimentally found rate law based on the mechanism, whichever one you determine is the rate determining step. The mechanism or the rate law for that step should match the one that was found experimentally. And if it does, then it's going to be a good mechanism. If they do not match each other, then it would be a bad mechanism. What is the rate determining step? The rate determining step is the slowest step in the mechanism. It is the one that basically determines the overall rate of the reaction. It is the person in the 10 items or less line with 400 items, right? You're not going to get through that line until that person gets through, right? He's your rate determining step right in front of you. And that's the idea here. There's going to be a step in the mechanism that's really going to be the slowest step in the mechanism. It's going to be the one, because it's the slowest step, going to, for the overall reaction, going to really be the one determining the rate and how fast or slow that reaction is going to take place. Hence our turtle I mentioned here. All right, so let's talk a little bit about how we can sort of determine these two things. So the experimental rate law for this reaction of NO2 and CO produce NO and CO2. The experimental rate law was found to be the rate is equal to K times NO2 squared. The reaction is believed to occur through these two steps. What is the overall reaction? So why don't you try that? What is the intermediates in this reaction? And what can you say about the rates of step 1 and 2? So why don't you take a few moments, give it a go, and then we'll talk about it, obviously, as to what's going on here. Okay, let's take a look. So we'll start with the first one, which is what is the overall reaction? So obviously in this case, that is going to be found by just simply, since we only have two steps here, we're just going to add these two steps together. Once again, anything that's on opposite sides of the arrow that's the same can cancel out completely, or it can even reduce down as well. So we have NO3 on this side and that opposite side, so they're going to cancel. We do have an NO2 here, and one of those NO2s will also cancel. And I think that's it. So at this point, everything on the left-hand side will stay there of the arrow, and everything on the right-hand side will stay there. That'll give us an overall reaction of NO2 plus CO. And then on the right-hand side, we have an NO and a CO2. Any questions all out there? Okay. What is the intermediate in this case? Intermediate is NO3. Anything else? NO2, CO2, CO, NO2. I'm just writing everything. I don't know. It's got that. I'm just writing everything. No, so it wouldn't be everything, right? So let's just see what we should maybe erase. Definitely probably should erase that because it just went on a tangent there. All right, let's talk about NO3. NO3 is an intermediate, right? It is there. It is there. But where is it not NO3? It is not there, right? So that is an intermediate. NO2 did get canceled there, got canceled there. Is NO2 still in the overall equation? It is. So because of that, it is not an intermediate. So an intermediate is something that is made early on in the mechanism, is not there when the reaction is done. It got to get used up. So again, you want to be careful on that. It should not appear in the overall reaction if it is an intermediate. So, but it should appear in the earlier steps, but get used up by the time it's done. Any questions on that there? All right, now we want to kind of think about what's going on in terms of these steps, you know. So I'm just going to erase some of my scribble here so we can kind of see what's going on here. All right. All right, so one other thing that was given to us in this particular sort of problem was we were given the rate law here that was found experimentally. This is sort of the experimentally found or observed rate law where the rate is equal to K NO2, and we're going to square it. Now, as I mentioned before, the only place where you could kind of write a rate law using the coefficients is in these elementary steps, which we have here. By the way, both of these elementary steps are bimolecular, right? They both have two things reacting on the left-hand side there. So for step number 1, if I wanted to write a rate law, the rate law would equal the rates equal to K, and this would be NO2 squared because that's NO2 and that's NO2. Another way of writing that is 2NO2, and that is where the 2 comes from, right? It's the coefficient that is there. We could also write a rate law for step number 2, which is the rate would equal K times our reactants, NO3 and CO in this case. So again, we're just writing a rate law based on the coefficients from these elementary steps of the reactants. Now, which one, in this case, should be the rate determining step or the slow step? Is it step number 1 or step number 2? How would I know? The rate law that was found experimentally should match the rate determining steps rate law, right? So is there a step that matches the one that was found experimentally? Yeah, the first one here has a rate law that matches the one that was found experimentally. And that means that in this particular example here, step number 1 here should be our rate determining step. That should be the slow step in the mechanism. So what that tells us is when we look at the rates of 1 versus 2, 1 should definitely be slower, right, than 2, right, in this case. 2 in this case would be more of the fast step in the mechanism, as it has a rate law that doesn't match the one that was found experimentally. Yeah. Yeah, so the slow step in the mechanism, the rate determining step, will always have a rate law if it's a good mechanism that matches the one that was found experimentally. So the slow step should always match the one that's found experimentally. Yeah. Yeah, so because step 1 in this case has a rate law that matches the one that was found experimentally, what that means is step 1 in this mechanism is what's known as the rate determining step, and the rate determining step is always the slowest step in the mechanism. So the rate of that first step in this mechanism is the one that's going to take the longest, and the second step in this mechanism will take a lot faster than versus the first part of the mechanism or reaction. Other questions? All right. Funness with